In this video, we will learn about infrared spectroscopy, or IR spectroscopy. We'll learn about how it works, kind of the fundamentals behind it, and then how organic chemists use infrared spectroscopy to learn a little bit more about the structure of the molecules that they're working with. So, for organic chemists, the big feature of IR spectroscopy is that it can be used to identify either the presence or the absence of certain functional groups. The way it works is it's looking at vibrational states. So molecules have many different vibrational states. I know we draw them on paper as static images, but actually the atoms are kind of vibrating around their bonds constantly, and all the atoms in a molecule are vibrating with respect to each other because there's always a little bit of kinetic energy in the molecule. So the common way that this is modeled is to look at just one bond at a time. So in the general chemistry view, that's to look at a molecule with just two atoms in it, or a diatomic. And the model for that is the harmonic oscillator model, where you kind of have this potential energy well. And so what you're supposed to view here is that a molecule can exist in any one of these kind of gray vibrational states. When it's in, for example, the lowest vibrational state here, the average distance between the two atoms would be located at this blue point right here. So I'll pull that down to the x-axis. And its vibrations in this lowest vibrational state can make it either be a little bit shorter or a little bit longer, right? So that's kind of vibrating a little bit. When the molecule here, or the bond, enters a higher vibrational state, then the average might move slightly, but then its range increases more, so it kind of vibrates further. And as you keep going up in energy, you kind of expect that there's harder and more vibrations. And the extreme end is that if you go really high in energy, you can vibrate hard enough to break the bond that's holding the atoms together. What IR spectroscopy is looking at is kind of the differences between these vibrational states of bonds and of molecules. The model for it looks like this, right? To show this in graphical form, we have two atoms on a spring. That spring can get stretched. In case it didn't really make sense there, the initial average bond distance is R. After stretching, we kind of become this distance R plus a displacement D. And on the harmonic oscillator, the D displacement would be viewed as that piece right there. Right? There is a bunch of math behind all of this. So kind of the first piece of it is that the energy is quantized. That's this kind of a I plus 1/2 piece right here. And it's quantizing the amount of kind of h nu that you have. The frequency of the light that would be related to one of these transitions is defined as this right here. It's 1 over 2 pi times the square root of two kind of more variables here. So this is the spring constant. This essentially tells you the strength of the spring, or in other words here, what we really care about is the strength of the bond. And then the bottom part, mu, there is the reduced mass, where the reduced mass is determined this way. So it's kind of the product of the two masses of the atoms on the bond and divided by the sum of those two masses. There's also kind of some physics reasons behind all this math, but in the end, all of this is folded together to get you to be able to calculate energy. So the entire principle of spectroscopy is that when the molecule absorbs energy, the molecule will enter into a higher energy state. And so in this case, it's the vibrational state. So again, a molecule that's at this blue point right here would absorb energy and enter into the next state up, or perhaps even the next state up, depending on how much energy was absorbed. That amount of energy is going to be related to a delta E, right? So that energy gap is a delta E, which would be kind of, you'd have an E1 minus an E2, or an E2 minus an E1 here. At the end of the day, it's still kind of a factor of this amount of light energy. The important thing that we can get out of the math is that our two variables that we can connect back to organic chemistry are the bond strength and the reduced mass. And so from that, we can say two things. So first, stronger bonds have larger spring constants, so they're kind of harder, there's harder springs to stretch. And if that's the case, then you need a larger frequency of light to be able to actually excite those bonds. That's because this is in the numerator. That should increase the value of the frequency here, overall increasing the amount of energy you calculate here. The second thing that we can get out of the math is that heavier atoms tend to increase the reduced mass, which is in the denominator of the frequency equation, and therefore the heavier the masses that are involved, the smaller the frequencies will be that are needed to excite those bonds. In a diatomic molecule, it's relatively simple to understand that you have two atoms on a spring and they're kind of going back and forth. So what does this look like for a more complicated organic molecule? Well, it turns out it's not too much more complicated. It's all the same type of thing where we are stretching bonds. So an exaggerated version of that is shown here, where this carbon-oxygen bond is getting stretched. And so what we're thinking about is that there is a certain vibrational state of this molecule where that carbon-oxygen bond is the one that's stretching. There's going to be other vibrational states of the molecule where, let's say, the carbon-carbon bonds are stretching or the carbon-hydrogen bonds are stretching. So there's kind of different vibrational so-called modes that are taking place. Just to give you another idea of what this might look like, another version of vibration would be a bending process where when you have kind of two bonds at an angle, they might change their angle slightly, and we call that bending. These are not the only types of vibrations that take place, but these are the more common ones that you'll see. There's two important comments to consider when it comes to these vibrations. One is that not every vibration will show up in IR spectroscopy. There is, for all sorts of reasons that are better suited for a physical chemistry class, there are all sorts of reasons that the vibration must change the molecular dipole in order for that vibration to show up in IR. And so what that means is that, for example, here we've kind of stretched this out. We've kind of pulled something in this direction that should change the molecular dipole. But if you have a very symmetric molecule and you were to stretch a symmetric molecule, let's say my pen is symmetric and I stretched it out and then let it back in, that would not be an IR active type of stretch. So we can only see a subset of all the possible vibrations in a molecule using IR spectroscopy. Secondly, the intensity of the absorption, so the kind of amount of the light energy that gets absorbed by a molecule at certain vibrational transitions, is related to how much of a change in dipole there is. So the more of a change in dipole, the more intense we tend to see IR signals to be. I'm going to pull up our two kind of pieces of intuition about bond strength and bond weight again, and then also this table of kind of very typical absorption ranges for IR. So let me walk you through what's going on here. The x-axis is presented in what's called a wave number. So it's a frequency term, but specifically it's given in inverse centimeters, and that's called wave numbers. You'll see it represented with this kind of a tilde over the frequency here. And the y-axis is often presented, almost always by organic chemists at least, presented as a percent transmittance. And so the thinking there is, if I have a sample and light is coming through, I'm trying to measure how much of this light got through. So if 100% of the light gets through, that means the molecule's absorbed 0% of it. So if the molecule doesn't absorb anything, then you should have signal 100%. If the molecule does start to absorb light, then you would have signal kind of look closer to zero, right? Closer to zero transmittance. And however much you are close to zero transmittance is related to that intensity piece that we just talked about. In general, the most important range for organic chemistry and IR spectroscopy is this range from 500 inverse centimeters to about 4,000 inverse centimeters. And from there, we can divide up little regions that are associated with different functional groups. This kind of smaller wave number region is called the fingerprint region. It's called that because it is very unique for every single molecule, but at the same time, every molecule has a lot of different signals showing up down here, which makes it kind of hard to be useful. So if you had a huge database and you were a computer, it'd be easy to mix and match things. But as humans, it gets a little bit hard to make any sense of the mess that you might see in this fingerprint region. So we tend not to use it very much. As you get to kind of the 1500 range here, you start to run into double bonds. Specifically, first you start to see the aromatic carbon-carbon double bonds at 1400 to 1600, and then you see just regular non-aromatic carbon-carbon double bonds at 1650-ish, and then at the closer to 1700 you start to see the carbon-oxygen double bonds. One thing you might notice here is that I'm writing these ranges down kind of in what seems like backwards order, so from a higher number to a lower number. That's because the x-axis in IR spectroscopy is almost always shown in this order, so from higher to lower. I think historically this comes from the fact that the inverse, or the wavelength, will go from low to high. But this is just a convention, so this is just how we're going to have to view the x-axis. As you go from carbon-carbon double bond to carbon-carbon triple bond, bond strength increases, so your frequency increases, so that's why this number is a little bit higher here. And then as the masses change, you start to increase in frequency again. So because hydrogen is so much smaller, that leads to a higher frequency. And what you have is kind of in this 3000s range is where all the various hydrogen to something else bonds are showing up. And so I think you can appreciate just by looking at this kind of simplified version that there are some kind of places that you can expect to see things, but at the same time it's not going to be immediately obvious whether you're thinking about a CH stretch or an OH stretch because their ranges overlap. So before we get into the practical side of using the IR spectroscopy, it's useful to try to understand why certain bonds show up in different places even though they look similar. So we'll look at a few of these patterns, starting with the carbon-carbon double bonds. So those were right here. And the contrast that I showed you was that the aromatic carbon-carbon double bonds are showing up in a different region, a lower wave number, than the regular carbon-carbon double bonds. And so important answer we should be able to come up with is to the question, well, why are they showing up in different regions when they're the exact same type of bond that we're thinking about? I guess the answer is that actually they're not really the exact same type of bond. So if I kind of show you two example molecules here, so just kind of a 2-butene versus benzene, we want to remember that our benzene ring being aromatic really in the resonance hybrid looks more like this, where those double bonds are delocalized around all 6 carbons like so, which means that we don't really have carbon-carbon double bonds, we have more like carbon-carbon 1.5 bonds. And because bond order is smaller, that means that all these bonds are going to be a little bit longer than a regular carbon-carbon double bond, and they're also going to be a little bit weaker, and that then means they're going to show up at a lower frequency than the regular carbon-carbon double bond. The next trend we'll look at is actually the trend within this range right here, so the carbon-oxygen double bond, or a carbonyl stretching region. And so this region is actually extremely useful because it helps us figure out, of the many different carbonyl containing functional groups, which one might we have. So I have a bunch of kind of extracted pieces of spectra here. So these are just the kind of 1800, 1700-ish region of the IR spectra of these molecules up here. What you see is that these are very intensely absorbing, so transmittance drops all the way to 0. So this is a trend. You'll tend to see that carbonyls have very strong absorptions, leading to very low transmittance. I wanted to show you here just kind of visually what it looks like. So this is an animation of the carbonyl stretch for the molecule of acetone, which is right here. There's not too much to see here other than the fact that those nuclei, the carbon and oxygen nuclei, are really stretching and vibrating a lot. Right? And so this is the process that we're thinking of when we look at a signal right here. This peak right here, or this valley, I guess, at 1715 in inverse centimeters, is corresponding to the vibrational state of the molecule that has the carbon and oxygen vibrating as in the animation. So within these functional groups here, there is a pretty big range, right? We're going from here, this is 1665 in the amide, all the way up to 1800 in the acid chloride. And the trend is not perfect, but there's two different things we can use to try to explain what's going on here. And so what we're really thinking about is that we're thinking about how the structure that is around the carbonyl piece of the functional group, how that structure is fine-tuning the stretching frequency of the carbonyl itself. So the two things that we care about are delocalization and then inductive destabilization. So let me walk through those here. So when we're thinking about delocalization, what we're thinking about is that part of the identity of this carbon-oxygen double bond is the fact that there's a significant resonance form, or that is like this, where we have kind of broken apart that pi bond to put a little bit more negative charge on oxygen, a little more positive charge on carbon. In this molecule of acetone, this is not too significant, right? However, if you look at the amide, it is much more significant that we can draw this resonance form where we can get a negative charge on the oxygen because we have a lone pair nearby from the nitrogen to kind of donate back in so that we don't have an unfilled octet in carbon here. So what I'm trying to say in all that is that if we're comparing the carbonyl in acetone versus the carbonyl here in this molecule, which is called acetamide, this carbonyl is going to have much more single bond character because its resonance form on the right here is much more significant. So we could think of acetone as having just a little bit of single bond character from the resonance form on the right. And so since you're gaining a lot more single bond character in acetamide, its stretching frequency for the carbonyl here is going to be at a much lower wave number. That's exactly what you see. That's at 1665 compared to acetone at 1715. This effect is balanced against a second effect, which is the inductive destabilization of kind of that charge-separated form of the carbonyl. So if you look at the acid chloride on the very left here, it has this very high stretching frequency of 1800. That's because when you think about the resonance form that has that charge separation, we have a problem of having a somewhat electronegative atom nearby that kind of really is fighting against that. So if I think about the bond dipole of the carbon-chlorine bond, the electronegative chlorine atom is making that bond dipole face this way. That puts two positive charges kind of closer together. That's not good, right? And so what's happening is the chlorine being here makes the resonance form where we've separated the pi bond onto the oxygen and carbon. The chlorine makes that resonance form less significant. So we see less of this resonance form in the hybrid. We see more of just the carbon double bond to oxygen in the hybrid. So that means we see a stronger bond, higher frequency in the IR. You can compare that against the ester here, where there's an oxygen next to that carbon. So oxygen is more electronegative than chlorine is, yet it seems like from stretching frequencies, it's not as impactful. And so the reason is because for the ester, there's two different effects that are operating. You have the delocalization effect, so you could draw an analogous resonance form for the ester, and that is moving the frequency kind of lower. And then at the same time, you have this inductive destabilization, where the inductive is referring to the electronegativity in working across a bond, and that's moving the frequency higher. So those two effects are kind of fighting each other and ends up having the inductive effect winning just a little bit by 30-ish wave numbers. As a final point, the difference now between chlorine and oxygen being here is that chlorine is in the third row of the periodic table while oxygen is in the second row. And because chlorine is in the third row, it has p orbitals that are not as able to delocalize with the carbon and the oxygen p orbitals, right? Because they're of different sizes. So oxygen in the ester has a much more efficient delocalization, so you get much better delocalization, bringing the stretching frequency down to 1740. Another very important region is the CH stretching region. So that's around the 3000 wave numbers area. And I have this gray line kind of drawn in here because it works out surprisingly well that this is a very hard cutoff between an sp3 carbon hydrogen bond and an sp2 carbon hydrogen bond. So I can pull up some data here. I have 4 different molecules. We have hexane, 1-hexene. This is kind of a 2-methyl, 1, 2, 3, 4, 2-methyl hexene, excuse me, and then here's benzene. So what we're trying to see here is where these stretching frequencies are showing up. So I know the font's a little small, but this number here is 3000. And so what you're seeing is all the CH bonds there are kind of piling up. All their different vibrations and stretchings are showing up here, right? So I'm just going to draw a couple of these CH bonds in here. Those are all kind of showing up in this less than 3000 region. That's this big peak right here. We can look at the same thing for 1-hexene here. So here again we have these sp3CHs. So those stretches are again showing up less than 3000, kind of like this. But then we also have now some of these sp2 carbons. Those are showing up here in the molecule, and those are the ones that are past 3000. It's really this one peak right there. And so if you didn't know what these molecules were, and I just gave you these two IR spectra, you could look at these and tell me that one of these seems to have sp2CHs and one of them doesn't. Cool. Same idea for this alkyne here. So this CH shows up at a little bit higher, so this is at 3300. That's that peak right there. While all those other kind of sp3CHs are showing up over in that peak, right? And here, definitely you get some relative sizing that's going on because you have many more hydrogens that are sp3CHs versus the one hydrogen that's an spCH. So that's why we see a bit stronger of a peak here. So there's kind of the intensity related to the dipole, and then also the intensity related to just the sheer number of bonds that are undergoing these stretches. Finally, in benzene here, what you see is that it only has those CH peaks past 3000. So that's kind of all this stuff right here. And there's kind of nothing less than 3000. And so that tells us whatever this molecule is doesn't have any sp3CHs in it. The other thing that you can see in this is that the aromatic CC stretch, the carbon-carbon double bond stretch, is right here. So that's coming from that right there. As to why this is the case, well, the reason for this is that we have to think about the amount of P character in the CH bond. So if the bond has more P character in it from the carbon, so like an sp3CH, that means it's a longer bond. And if it's a longer bond, we'll think of that as a slightly weaker bond. So an sp3CH should have the longest CH bond. That means it's going to be the weakest bond of these three kind of options here. And that means it's going to show up at the lowest stretching frequency. That's exactly what we see. sp2 should be the next highest one because it's got a little bit less P character, a little more S character. That makes it a shorter bond, a little bit stronger bond. Now it's showing up a little bit past 3000. Then you go to sp, and again, that's going to become an even shorter bond, an even stronger bond. Now that's showing up at 3300 here. So the hybridization state of the carbon is one way we can explain what's going on in this trend. Now let's look at the OH and NH stretches. Those tend to show up as broader peaks, right? So the carbonyl stretches were very narrow peaks. The CH stretches were maybe a little bit broader, but the kind of the OH and NH type of stretches will show up really broad. So if you're looking at kind of this big mountain here, or this mountain right here, kind of this peak right here is your NH, and for this molecule, actually this one right here is. So if you're looking at these, one pattern that shows up is that if you have an NH2, then you'll see kind of a fork pattern right here. So there's two peaks right next to each other. That's related to the fact that the two hydrogens can either both go stretch at once or just one of them can kind of stretch at a time. And so there's two slightly different energies associated with that, so you get two peaks. Whereas if you look at the secondary amines, you only have one NH bond, so then there's only one possibility, so you only get one energy at which we're detecting that stretching frequency. Same thing for the amide here. If we look at an alcohol, same idea, right? We get this really kind of broad looking peak. There's only one OH bond that can stretch, so we only get one peak here. You tend to see that alcohols are a little bit broader than the amines. So that can be maybe a way to tell. So for example, if you look up here, this seems to be kind of a narrower looking peak than this alcohol one here. So if you're observing this astutely, you might notice, well, why is there kind of this single little peak way out here close to 4,000? Is that meaningful or not? And it turns out it is. And the confusing part here is that there are two different OH stretches that show up. There is the big broad one that I already pointed out, which is right here, and then the little kind of sharp one that's right there. And these are both related to the alcohol in the hexanol molecule. The difference is that we're seeing actually the hydrogen bonding effects that are showing up. So the reason we get some really broad peaks for alcohols and amines is actually because we're doing a lot of hydrogen bonding with these molecules. Those NHs are going to be hydrogen bonded to other things that are in the sample. And whenever you have a hydrogen bond, you kind of are slightly affecting the stretching frequency of the NH bond that you care about. And so each hydrogen bond will be slightly different. And over the range of, moles and moles of molecules, you're going to have some of those hydrogen bonds be a little bit stronger, weaker, all depending kind of on how randomly those molecules are distributed in space. So hydrogen bonded OHs and NHs again will show up really broad. But if for whatever reason the molecules happen to be free of anything else, they just happen to not be hydrogen bonded, then those OHs will show up as nice, sharp single peaks that are high in frequency. So hopefully it makes sense that if you have an OH and its hydrogen is being hydrogen bonded, what's really happening is that the oxygen and the hydrogen are becoming weakly bond together in order to gain a bit of bonding with another atom. And so since we're losing some of the bonding here to gain hydrogen bonding, that's why the frequency of the broad peak is a little bit lower than the frequency of the sharp one, where it's just the OH by itself with no hydrogen bonding. And so that's something important to keep in mind, that the data that you see in an IR spectrum is context dependent. And so the reason we know that is that we can take the same molecule, hexanol, put it into the gas phase where it definitely is not doing any hydrogen bonding at all, and take an IR, and what you see is only that one sharp signal. Right? You don't see any of the broad signal because in the gas phase molecules are all separated from each other. Just to give you a frame of reference, the data on the left is from a sample of hexanol that's 10% in a tetrachloromethane solution. So 10% of the molecules in this sample are hexanol, and what you're seeing is that the vast majority of them are hydrogen bonding. So just get the words on the screen again. Some key observations here are the NH2 peaks will come up as two little peaks, and hydrogen bonding tends to really lead to these really broad peaks. We'll look at two more important trends. One of these we saw in some sense, but in a different version with the carbonyls. So the first one here is that conjugation to a bond that you're looking at tends to reduce stretching frequency. So if I'm thinking about this carbonyl, or I'm thinking about this alkene, then the fact that they're conjugated together is going to make both of them have lower stretching frequencies than I would expect otherwise. The reason for that is because we have a significant resonance form that looks like this. That significant resonance form has less double bond character on this bond, less double bond character on that one. Right? So we would expect to see these show up at lower frequencies. There's nothing like evidence, so we can look at a series here. And so I would look at these and say that the rightmost molecule has no conjugation to the carbonyl. Right? This is just a regular ketone. The middle molecule has a lot of conjugation here. This double bond's entirely conjugated with the carbonyl and nothing else. The aromatic molecule on the left here is actually going to have less conjugation to the carbonyl because the double bonds in here are kind of splitting their conjugation. So you could think of it as like it's conjugating a little bit outside here, but it's also conjugating to be aromatic. So then we'd expect less impact on the stretching frequency. And the numbers bear that out. The just regular ketone, 1724. The aromatic one here, so the somewhat conjugated version here, 1692, so there is a shift. But when it's kind of more delocalized, then you get 1667. Again, this is for the carbonyl stretching frequency. And so there's a nice rule of thumb that kind of each piece of conjugation, so a double bond of conjugation is supposed to be worth about 30 wave numbers-ish. And so, and this is a very big generalization because there are a lot of other factors that can weigh into all of this. But if you see a number that's 30 lower than you expect for a certain functional group, you could predict that that functional group might be conjugated. Another thing that shows up is that if you're dealing with different ring sizes, strain can change the frequency at which a functional group stretches. And that's because you are forced to enter into kind of non-ideal hybridization states to accommodate all that strain. So the kind of example that everyone looks at is when you have a ketone that's part of a cycloalkane. So these are called cycloalkanones because it's an alkane with a ketone in it. And so of course the smaller the ring, so 3-membered ring here, the more strained it is. 6-membered rings tend to be the least strained of them all. And so what we kind of see is that as the carbonyl is in more and more strain, the stretching frequency of the carbonyl goes up. And this is related to this idea that as the bond angle here at this carbon gets less and less ideal, the kind of solution from a molecular perspective is to try to lengthen these bonds a little bit. And to lengthen these bonds a little bit, we have to take p character and put it into these endo bonds, so these endo bonds within the ring here. And in making these bonds a little bit longer to help with that strain, we are forced to make the outer carbon-oxygen bond a little bit shorter. That increases the bond strength because we have a shorter distance between atoms. That then increases the stretching frequency. So again, we have this rule of thumb that if we're dealing with a carbonyl that's in kind of this ring like this, then each kind of decrease in ring size by one atom will increase stretching frequency by 30 wave numbers, approximately. As you're first learning about spectroscopy, and IR specifically, it can be very hard to keep track of all these numbers and exact locations where we expect to see things. So there are plenty of data tables that can be found that kind of try to lay out where various functional groups will show up. This is one of them right here. This one's just a nice infographic version. And there is another one that I have here. This one is a kind of a more typical way for these data tables to show up. And just to kind of explain what's going on here, what this is showing you is that for kind of a typical IR, the X location where a peak might show up is given by these black bars here. The kind of spacing on the vertical axis means nothing in these data tables. It's just to make things fit. All you really care about is the X-axis position. So it's important to remember that these are ranges and that these ranges are a little bit flexible. So they're helpful, but they can also be imperfect. So for example, my bottom table here, these are ranges given for typical carbonyl functional group stretches. And right away you can see that the carboxylic acid, ester, aldehyde, ketone, amide, they all kind of could potentially be in certain regions, right? And so the way I use these data tables is to say I'm going to take the average or the center of this range, have that be my baseline in my head, and then work from there. So if I see a carboxylic acid is usually, and at the center is around 1700, if I see that it's at, let's say, 1670, then I think in my mind, oh, that might be because it's a conjugated carboxylic acid. Likewise, if I see the ketone that's supposed to be at like 1720 and I see it showing up at like 1740, then I might think to myself, maybe it's strained. So with all this, there's kind of two things that we want to be able to do. We want to be able to take a given molecule and know where to look for significant peaks, so to know where to look for functional groups. And we want to be able to take a piece of data and figure out what functional groups might be in the molecule from which the data was taken.